Hello again, guys. Can you remember last lesson we worked out that the solar energy being absorbed or going into planet Earth was 239 watts per square meter. Now, if we assume that the Earth is staying at the same temperature, this must mean that the outgoing radiation must equal the ingoing radiation. So the outgoing radiation out must also equal 239 watts per meter squared. Now, if the ingoing radiation was more than the outgoing radiation, that means the temperature of planet Earth would heat up. Now, if the ingoing radiation was less than the outgoing radiation, that means the temperature of the Earth would cool down. But generally speaking, the planet Earth is staying at the same temperature, and so we have a situation like this. We have 239 watts being absorbed by planet Earth and 239 watts coming out of planet Earth. And the satellites can measure roughly this 239 coming out of planet Earth once they take into account the surface area of the Earth. So this measurement is known as a top of the atmosphere, TOA, as top of the atmosphere measurement. Can you remember this picture? It was during the lesson about black body radiation. So these individual curves, they show what the temperature of a body is. For example, this curve is 4,000 degrees Kelvin. But I also said that the area under a curve corresponds to its energy. So if we know what the temperature of a body is, we know how much energy it is emitting. So let's go back to the other picture. So also it's true to say, if we know how many watts per square meter is being emitted, we should be able to work out the temperature. And it works out that 239 watts per meter squared corresponds to a temperature of about 255 Kelvin, which actually equals minus 18 degrees centigrade. So that's very strange. Just by looking at the energy leaving planet Earth, and this has actually been measured by satellites and everything, so we know it's correct. It says that the temperature on Earth should be minus 18 degrees centigrade. So, well, obviously it's not minus 18 degrees centigrade, is it? It's about 15 degrees centigrade. So, what's gone wrong? So, let me clear all this away, and then I'll explain it to you. Okay, a new diagram. Now, we said that the energy flux going out at the top of the atmosphere is 239 watts. And that corresponds to a temperature of 255 degrees Kelvin or minus 18 degrees C. And we know that's, in real life that's too cold. The temperature of the Earth isn't minus 18 degrees C. So let's work it back the other way. We know that on Earth the temperature is plus 15 degrees C, which is 288 degrees Kelvin, which corresponds to an energy flux out of 390 watts per meter squared. So this should seem even more strange to you, because we said that the energy coming in at the top of the atmosphere was 239, but somehow the energy coming in actually manages to heat up the surface of the Earth to 390 watts per square meter, and then but by the time it goes through the atmosphere, it's reduced to 239 watts per meter squared. So what's going on here? Well, what's happening is it's all down to the atmosphere. If I draw the atmosphere here, let's pretend that this is the atmosphere, a very, very simplified atmosphere. So now the long wave radiation leaves the surface of the Earth and goes into the atmosphere. Because of the greenhouse gases in the atmosphere warms up, and then when the atmosphere warms up, it does two things really. It continues to radiate heat upwards, but also, because the atmosphere has warmed, it will also radiate heat downwards again. And some of this downward radiation heats the surface of the Earth again. So that's the reason why we have a difference between the energy leaving planet Earth at the top of the atmosphere and the energy leaving the surface of the Earth. So let me just repeat that again. We want to find out why is there a difference between the amount of energy leaving planet Earth and at the surface, and why it's different to the energy leaving at the top of the Earth's atmosphere. And the reason is long wave radiation, it leaves the surface of the Earth and then it will heat up the atmosphere, represented by this block here, and then some of that heat will then continue to space, to be lost at the top of the Earth's atmosphere, but most of it gets radiated back down to Earth again, like this, where it actually heats the surface of the Earth to make the surface of the Earth higher than at the top of the atmosphere. So it's warm, the surface of the Earth is warmer at the surface than at the top of the atmosphere because of the atmosphere. Now actually this diagram is a little bit of an oversimplification. It's much better to, instead of imagining just one block of atmosphere, it's much better to imagine that the atmosphere is made up of, for example, lots of blocks, something like this. And that each block is reacting with the one which it is beside. For example, long wave radiation is going up into the first block, then the first block radiates some of that energy back down to the ground again, right? But also it also radiates some of its energy into the next block. The next block radiates some of the energy back to the original block, but also it radiates it to the next block of atmosphere above it, and this continues all the way to the top of the troposphere. So another way of looking at this is, if there were no atmosphere, because of the distance that the Earth is from the Sun, the Earth would normally be minus 18 degrees centigrade. But because of the atmosphere and because of this process here, right, the Earth is a very pleasant 15 degrees centigrade, and we're all very, very happy about that. Okay, so I hope you understand that, and I hope that's all clear. If you don't understand anything, you can always ask me in class. Okay, see you next lesson. Bye.